Hey folks, this is our second installment of Climate Change, the Basics. In part two, we're going to look at how greenhouse gas concentrations and temperature change over geologic time and recent time kind of go hand in hand. And this helps, this is part of the evidence that led climate scientists to understand the relationship between greenhouse gases and climate change last century as we were learning about this. So let's get started. Okay, this graph looks a lot like the graphs that we saw in part one. They're set up very similarly, where we've got a timeline that starts from 800,000 years ago and goes up to the present time today. So therefore we are looking at a time period of the Pleistocene, the ice ages, and also the Holocene in these last 10,000 years here at the very end. And similar to before, you've got a blue line that's going up and down, and it's really jaggedy looking, but you see some wave action to it as things go along. What's different is that instead of mapping temperature change, we're mapping carbon dioxide levels in terms of what are called parts per million, or ppm. You're going to see ppm a lot in our learning about climate change. ppm stands for parts per million, as I said. This is a measure of the concentration of carbon dioxide in the atmosphere. So that's basically saying of 1 million molecules taken out of the atmosphere, how many of those million are carbon dioxide? That's basically what parts per million means. And you can apply that to any greenhouse gas or any gas it's in the atmosphere. Or in a liquid, you can do the same kind of measurements for liquid. Okay. So what I want you to notice here is that with these carbon dioxide levels, that they go up and down like we saw with temperature change during the Pleistocene. And in fact, if we look at our next slide, let me regain control of the, hang on just a second. Okay, sorry about that little glitch. Learning to use this software is challenging. Let us just say that. So this new slide is showing the same slide we saw before. So we're looking at carbon dioxide levels up here on the top graph. And now on the bottom graph, what we have is temperature. So it's for the same time period. So 0.8 million years is the same as 800,000 years ago. And so these are the same timelines matching up side by side. And what I want to draw your attention to is what climate scientists noticed and geologists noticed, is that the peaks for a warming interglacial period during the Pleistocene correspond to peaks in carbon dioxide. So up at the top we've got carbon dioxide, on the bottom we've got temperature change. And we see that over and over again where the peaks match up. As you see there and there, and even in the more recent interglacials and the time. And of course, I'm highlighting here the times when it got really warm, but you'll also see during the times where it got really cold. So this would be like one of those ice ages here. That also corresponds to a time when carbon dioxide levels were lower here. All right. Now you might be wondering how we know that the carbon dioxide levels were at these different rates or different concentrations in time. And as it turns out, this is coming from data taken from what are called ice cores. This is where we go to places in the world where we have glacial ice that's built up over hundreds of thousands of years. And as layers, I'm trying to illustrate this with my video of myself, as layers of snow fall on the glacier in layers, much as the same way that sedimentary rock builds up, these layers of snow that fall down, they show the sequence in time, so that older layers of snow are at the bottom and newer layers of snow are at the top. And I say snow but it doesn't take long for that snow to turn into ice, especially as it's compacted underneath layers that are stacked up above. And interestingly, as the snow falls on these glaciers, they wind up trapping little tiny bubbles of atmosphere. So if you look at an ice core, you would see a solid block of ice, and embedded in that would be these little spheres of atmosphere that are trapped. Well, climate scientists have the tools where they drill into these ice cores and extract those little bubbles of atmosphere, and then can analyze the chemical composition of that atmosphere to look at levels of carbon dioxide and other gases in the atmosphere at that time. And that's how we're able to reconstruct these graphs that show carbon dioxide change and temperature change. Temperature change data is from other sources, not from ice cores. It's using everything from like tree ring data to growth rings and corals, ancient corals that were preserved, and even sometimes sedimentary rock or sediment soil formation. So there's lots of different things that have led to the graph that you see on the bottom. Okay, so this next slide is to illustrate how and what was driving the ice ages. Because if today we're talking about climate change and we're talking about a lot of warming happening, we've seen a lot of warming happening in Earth's past, and even including the recent times during the Pleistocene. And I've got those little bubbles up at the not those little bubbles, but those graphs up at the top right that we saw before, where we got carbon dioxide at the top and temperature at the bottom. And all of this is to show not only the correlation between carbon dioxide and temperature, but to explain why and how these things are connected. Okay? And what we know now about climate change during the Pleistocene is that it was triggered by changes in Earth's rotation around the sun and Earth's rotation around its own axis as it spins. And these variations in these rotations are called Milankovitch cycles. Okay, and we see the illustration here at the center. So here's our Milankovitch cycles over down here on the slide. And there's 3 different ways that Earth's movement around the sun can change. Sometimes Earth's orbit is more circular, like you see with the circle that I just put the red dot on. And sometimes Earth's orbit around the sun tends to be more elliptical. And that ellipse can also vary in a way such that the sun is not at the center of the ellipse. You'll notice that the distance between the sun and the left edge of the ellipse is different from the sun and the right edge of the ellipse. And of course, these circles represent the pathway that the Earth takes around the sun to make one solar year. That's 365 days in our time. Okay, so that's one form of Milankovitch cycles. And all that to illustrate that during times when Earth's orbit is more elliptical, the Earth spends more time way out here away from the sun. Notice how far that is away from the sun compared to, say, over here. And that means that Earth has a significant time of the year when it cools down and gets kind of cold. So during phases of Earth's history when our orbit around the sun looks like that, we tend to get cooler than in other time periods. Now, other ways that Earth's orbit change include changes in our obliquity, as you see here. Okay, obliquity has to do with how oblique the Earth's angle is relative to the sun. So here we see the dotted lines here represent the axis around which the Earth spins once every day. Well, that axis can be sometimes at an angle that's the different point in the night sky or out in space. We just see it at the night sky because we can see which direction we're pointed to in terms of the stars. During some times of Earth's history, Earth is more upright, as you would see here with the arrow that I've indicated here. And at other times in Earth's history, our angle is more oblique. And when we have these more oblique angles, that means that during the winters, the the Earth tends to get much colder because you have much more of the Earth's surface angled away from the sun, and so that allows for a significant degree of cooling down. And then finally, there's variation in what's called precession, which is how the Earth's axis is tilted into space around the sun. So right now, Earth's axis is more or less pointed towards the North Star, but at other times in Earth's history, it's been pointed towards other stars in the sky, such as Vega that you see here. The point of this is that when Earth is pointed towards the sun, or pointed more upright, we tend to have warmer time periods, and when we're pointed more away from the sun, we tend to have times when the Earth can cool down and get a lot colder. So anytime these Milankovitch cycles happen at the same time, such as when you get eccentricity leading to cooling, and obliquity and or precision leading to cooling, you get times when Earth gets really cold relative to other times. Okay, so these Milankovitch cycles we now are able to plot out in time, because Earth's behavior is predictable in the way that we orbit around the sun and spin around our axis and point towards different points in the sky or out into space. And so it turns out that these cycles largely correspond to the cycles that you see up here, where you've got the different interglacial periods and the different glacial periods, such as I'm circling up there. So we now know, having pieced all this together, that the Pleistocene ice ages were driven by these Milankovitch cycles. And if that's the case, you might be wondering, well, why did carbon dioxide levels, why did these go up and down over time? If we know that carbon dioxide is a player in terms of influencing temperature, what's the connection? Well, as it turns out, what happens is, as the Earth warms or cools, it causes the oceans to either release or absorb carbon dioxide. And during time periods when the Milankovitch cycles lead to warming, it allows the oceans to release carbon dioxide from the oceans. And when it releases that carbon dioxide, that means that the atmosphere is able to trap even more heat. So it starts a whole, a Milankovitch cycle will trigger the initial warming, and then that triggers a release of carbon dioxide, which causes even further warming. And that's what leads to leads to the time periods during the Pleistocene when carbon dioxide levels would go up, and temperatures would continue to go up as well. And then the Milankovitch cycles would lead to a cooling down. The oceans absorb and hold onto that carbon dioxide, and temperatures would go down, and CO2 levels would go down. So the two kind of go hand in hand. It's like it's like two partners dancing, like in a ballroom waltz kind of situation. With, in this case, temperature leading at first, and then carbon dioxide leading second. I guess that isn't really a good analogy with dancing, because you have one person that leads and the other doesn't, but I think you get the drift. That the long and short of this is that Milankovitch cycles are what have driven these changes in Earth cycles during the Pleistocene. Okay, what I wanted to talk with you about next is that there's a variety of different greenhouse gases, and they're not equal in their ability to trap heat. So here we're looking at a table that shows 4 different types of greenhouse gases: water, carbon dioxide, methane, and nitrous oxide. These are some of the ones that trap the most amount of heat. Now, carbon dioxide is the one that you hear the most about. And CO2 is a pretty simple molecule. It's one carbon atom surrounded by 2 oxygen atoms that you see here. And this is the one that is having the biggest impact on the warming of the climate. That said, relative to these other heat-trapping molecules, it doesn't trap a lot of heat at the individual molecule level. So if we were to talk about units of heat that each of these molecules um, can absorb, one unit or one molecule of carbon dioxide can absorb 1 unit's worth of heat. Okay, and in fact, this way of like comparing greenhouse gases for their heat trapping impact is based on just making carbon dioxide unit 1. Okay. The second thing to notice is that over here in this next column is methane. Methane is also known as natural gas. This is the kind of fuel that we use in kitchens, in some kitchens that use gas for cooking. It's often used for hot water heaters and also for heating homes and that sort of thing. Methane is very potent greenhouse gas. Notice that one molecule of methane will trap the equivalent of 21 molecules of carbon dioxide. So in other words, one methane molecule is 21 times worse at trapping heat, or maybe I should say better at trapping heat than carbon dioxide. So a third way of saying this is to say that it would take 21 carbon dioxide molecules to trap the same amount of heat as one molecule of methane. Okay? Methane's a big deal because we use it a lot. We're doing a lot of fracking in order to get it out of the ground. Fracking is a form of mining. And in the process of pulling it out of the ground and piping it to our homes and businesses and so forth, a lot of methane is emitted into the atmosphere and traps a lot of heat. There are other sources, including cows. We'll talk about this later, but cows belch a lot of methane because of their digestive processes. And it turns out weird things like termites, also termite colonies emit a lot of methane. Okay, moving on down the line here, you see that methane, while it looks like it's a real bad guy compared to carbon dioxide, and it is, it's not nearly as bad as nitrous oxides. Nitrous oxide molecules trap 310 times more heat than does one carbon dioxide molecule. So nitrous oxides, where do these guys come from? Well, they come from the burning of fossil fuels. It's one of the main pollutants that we get from burning fossil fuels. And so as we burn fossil fuels, we're not only adding carbon dioxide to the atmosphere, but also nitrous oxides, with the exception of when we're burning methane, because methane in its pure form will not release nitrous oxides, but it's got to be a clean form of methane in order to do that. We'll talk more about that later on. Okay, one of the ways that we know that it's the Industrial Revolution and that it's humans that are causing greenhouse gas accumulation in the atmosphere is these curves. What these curves are showing us is concentrations of greenhouse gases in the atmosphere since the mid-1980s. Up at the top, we got carbon dioxide. To the top right, we've got methane. And at the bottom center, we got nitrous oxides. Okay? And what you see in all cases is that these curves are headed up and to the right. That means that over time, which is moving to the right on the x-axis, the concentrations of these molecules in the atmosphere are increasing. So that means that over time we're seeing more and more of these greenhouse gases accumulating in the atmosphere. And this has been going on ever since we've been measuring this, which goes back in time far, far back before the 1980s. This is just the last few decades looking at this. This is again more evidence that we humans are changing the chemical composition of the atmosphere, and therefore are the ones that are behind the changes in global temperatures and all the other changes that are happening with climate change. Okay, this is our final graph for this unit, and what this is showing is the combination of carbon dioxide concentrations in the atmosphere since the 1880s. That's what we see here represented with this dark blue line that goes across the graph, this line that starts right here. I'm going to draw an X on it. Okay. Hold on. Sorry about that. My computer's misbehaving again. What we're seeing here is carbon dioxide concentrations since the 1880s over time up to the current or very recent years. And we see that there's a strong upward curve. It starts here down at about 56.5. I'm sorry, about 200, and I got to read the y-axis on the right-hand side over here. Roughly 290 parts per million of carbon dioxide in the year 1880 to up around 395 here around the year 2010 or so. Okay, so carbon dioxide levels have risen dramatically since the beginnings of the Industrial Revolution. At the same time, temperatures have changed as well, and that's what's represented here by these really tightly packed bar graphs. Now, this is kind of a complicated graph to show temperature, so let me explain what's going on here. First of all, we read the temperature over here on the x-axis here, and it's in degrees Fahrenheit in this case. Sometimes we'll be looking at Fahrenheit, and sometimes we'll be looking at Celsius. Depends on what the authors of the graph wanted us to see. And this right here, you'll see this line that goes across the page all the way across here. This is basically it's a reference line. It's kind of arbitrarily set. Probably in this case, if we read down through the fine print at the bottom, it's the black line shows atmospheric carbon dioxide concentrations in parts per million. Okay, I'm not reading fast enough to pick up on it, but it usually is like picking some year and times. Oftentimes it's around the year 1960 or so, and saying, okay, let's that be the baseline year for comparison. In that case, any time where temperatures were below, what is it, 57.1, looks like 57.1 reading the axis here. Anytime temperatures were below that level, they're going to show up as bars that drop down, and they've color coded them blue, meaning that they're cooler years. That's what all these lines are that I'm indicating down here. Any of the red bars that are stacked above this central line are indicating years where it's warmer than that overall average. And they come up with this average here of the 57.2 based on, for example, the average global temperatures between 1880 and the year 2010 or whatever it is, unless they used a reference year like we talked about. And again, I can't, let me read it real quick and get clear on that. Okay, after reading the figure legend down at the bottom, it doesn't really specify like how they created that reference line there, but based on the way they're talking, I think it's the average over this time period, okay? But it doesn't matter, because really what we're trying to illustrate here is that over time, temperatures have gone up in more or less at the same time that carbon dioxide concentrations have increased. And we've seen both of these graphs before on other graphs that I've shown you. If we were to illustrate what the overall temperature variation is during this time, I could just sort of connect the tips of these bar graphs like this, and we'd see a bunch of slop in here, and then it goes up like that. So the red line that I just superimposed on here, and if I was smarter than I am, I would have chosen a different color, right? What that is illustrating is the overall temperature change during from 1880 to just a few years ago. And what we see is that as carbon dioxide levels are going up, also temperatures are going up. It's not a clean and perfect relationship. There's some messiness to it, but especially since the mid-1980s or so, that relationship has been very linear. And let me erase all these markings on here so you can see that. So especially over the last few decades, it is a very strong relationship between temperature increase and CO2 increase. All of this is part of the strong evidence that we have that there's a connection between greenhouse gas concentration in the atmosphere, specifically in this case carbon dioxide, and rising temperatures globally. Okay, so what then are temperatures today in the atmosphere? Let's check because I just looked it up this afternoon. Okay, there are numerous websites where you can go and it will tell you what the carbon dioxide levels are at for at right now and at any time in the recent past. And this particular website on this today of making this video is April 2nd, 2020. And so this is basically how much carbon dioxide was measured in the atmosphere yesterday on April 1st, 2020, and that's 415 parts per million. And this was measured in Hawaii. It's one of the places in the world where we have really clean air, and the air of the planet tends to get really mixed up very well over the Pacific. And there's a really tall mountain, Mauna Loa in Hawaii, where they have an observatory at the top where they measure atmospheric carbon dioxide and have been measuring it for many, many decades now. So it's one of the reference points, one of several reference points we have on the planet for measuring carbon dioxide levels. And that's what this is from these observatories where and why we have the more recent data that show these really tight relationships between carbon dioxide and temperature, because we have much better data over these last few decades. All of this to point out that over the last year, and you see this here, the final thing that I'll circle here, over the last year there's been an increase in 1% of carbon dioxide in the atmosphere. So we added 4.12 parts per million out of roughly 412 parts per million if we were to average these 2 years. So all that to show that atmospheric carbon dioxide levels continue to increase. Okay, so let's do a quick wrap up here before we're done this particular video. We've talked about already how global temperatures have changed through Earth's history. We've looked at temperature change in recent history, and now more recently we've looked at in this second part we've looked at carbon dioxide levels and other greenhouse gases. We understand how those greenhouse gases work, and we've looked at how their concentrations have been accumulating in the atmosphere as a direct result of the burning of fossil fuels to power the industrial economies of the world. What we're going to do next is take a look at what some of the impacts that we're seeing on the planet. So that'll be coming up next.